here, as far as the structure of the sarcomere, we said it's the functional unit of muscle. It is bordered by two Z lines, and Z lines may sometimes be referred to as Z discs. They're the same, they're synonymous terms. And so essentially, as a part of the shortening of the sarcomere, we've got these two filamentous proteins, actin and myosin. These are also sometimes called myofilaments, myo meaning muscle. So they're collectively referred to as myofilaments, but they're thin filaments, actin, thick filaments, myosin, that are essentially interweaving themselves longitudinally as a part of this sarcomere, and they are sliding past each other in order to shorten the sarcomere, which is bringing the Z lines closer together and shortening the entire myofibril overall. So when each of these sarcomeres are shortening, the entire myofibril shortens, and then the rest of the muscle body eventually shortens. And so these are the events that we began describing. So we were talking about the proteins here, the structure of those proteins, and just to remind ourselves, because we're going to get into this a little bit later, we talked about the binding site on actin for the myosin head, and we spoke about the binding site on, let's actually look at this here. So the binding site on actin, so these black dots for the myosin heads, and then the binding sites on myosin where it will bind to actin. So the actin binding sites on myosin. We also referred to or talked about the ATPase site on the myosin heads as well. This is where ATP will bind, and this is going to provide the energy for the movement, okay? So that's kind of where we're going to pick up here today and actually get into the details of this sliding filament model. So we'll talk about the sliding filament model. We'll talk about cross-bridge cycling, which is an important aspect of that sliding filament model. And this is how muscles generate force. So muscles not only shorten for movement, so not only to just move my limbs, you know, movement all over the body, but muscles also shorten to generate force. This is how we can lift objects. This is how we can, you know, move things, physically move other things by that force generation that's brought about by the cross-bridge cycling. We're also going to speak about excitation contraction coupling, which is how we regulate this process, how we turn it on and off via calcium, really, really important. And then we'll talk about muscle metabolism in packet 2. So we won't get to muscle metabolism in this packet, but it'll be a part of packet 2. So what is the sliding filament model? And let's kind of remind ourselves that this is a model because no one has visualized this, right? This is a theory about how muscles shorten based upon visualizing histologically the staining patterns of the sarcomere under the microscope. So we visualize how the sarcomere goes from a lengthened position to a shortened position. And then we come up with this model about how this shortening actually takes place. So we know that there are these thick and thin filaments that are overlapping. And I talked about this a little bit before, but we've come to the understanding that our initial suspicion, so the theory that an earlier physiologist had was that the filaments were shortening, that they were shortening in and of themselves, and that was what brought about the shortening of the sarcomere. We've now dispelled or disproven that, and so what we've come to understand is that there's not shortening of the proteins, neither are both the proteins energized separately, if that makes sense. So actin is not moving itself, myosin is doing the movement, right? So what's happening is that the filaments are really sliding past each other. And it's more correct to say, other than saying that they slide past each other, it's more correct to say that myosin is actually dragging actin. So myosin is the energized protein in this process, and myosin is the one that's dragging actin in the opposite position, moving itself in another position, and then dragging actin again. And we'll talk about how all of that occurs on a subcellular level here. So let's speak about what's happening to our bands and zones as this sarcomere shortens, as the sarcomere contracts. So just to remind ourselves what these bands represent, the I bands we said were only thin filaments, so only actin, and they were anchored together by the Z line here at the center of the I band. The H zone, we said, was only thick filaments, also anchored together at the center with the M line, although that's not shown here. And then the A band was the area of overlap. So the area where actin and myosin were overlapping, that is what we refer to as the A band. And we can differentiate it because it stains a little bit darker as it has the presence of both of these proteins as opposed to just one of the proteins. And so as the sarcomere shortens, we see that the thin filaments move closer to the M line. The thin filaments, are being dragged rather closer to the M line. The thick filaments are moving closer to the Z line. And so the Z lines are coming closer and closer together, okay? And so if we look at our bands, the I band is going to shorten. Remember, the I band is the area of only thin filaments. So as the area of overlap increases, as actin moves closer to the M line, the area of only actin is obviously going to get smaller. So the I band shortens. The H zone likewise also shortens. So the H zone, the area of only thick filaments, will get shorter or smaller because as the area of overlap increases as actin moves towards the M line, the area of only thick filaments will obviously also get shorter. The A band does not move, right? The A band does not change its length rather. So the A band stays the same size. And that's because the A band represents the area where actin and myosin are overlapping. And because the size of myosin, the size of these thick filaments, the H zone is not the H zone, the A band essentially, because that doesn't change, the length of myosin doesn't change. Remember, we said that they're not shortening. If they were shortening, the A band would also get smaller. But because they're doing the sliding motion and they're not shortening, the A band, the area of overlap, actually remains the exact same. Okay. And so as all of this is happening, the Z discs are getting closer together and the entire sarcomere is shortened. We can also appreciate that the A bands of other sarcomeres are getting closer to the A bands of their neighbors, essentially. So the A bands of the neighboring sarcomeres are getting closer together as the Z discs get closer to the other Z discs, if that makes sense. The entire thing is shortening. This sliding is due to what we call cross-bridge cycling. And we described what the cross-bridge is. It's the heads of myosin that are sticking up. And if we remind ourselves of the structure of myosin, we've got these golf club-like structures with the two heads that are sticking up, and they're kind of intertwined with each other. And they've got those two sites that we talked about, one for ATP, one for actin. And so those are the cross bridges that are sticking up. They are going to make contact with actin. So they're going to reach up, bind to actin at that site. When they make contact, myosin is going to drag actin towards the M line, towards the center of the sarcomere. They're then going to break contact. Myosin is going to reposition itself to a new spot on the actin filament, make contact again, drag it again. And that's going to happen over and over until the entire sarcomere shortens. So it's not one large go where the entire thing shortens, but it's a series of cyclical making and breaking interactions and dragging, gradually until the entire sarcomere is shortened. And that's why we refer to it as a cyclical process, because it's happening over and over and over again for the sarcomere to shorten. So that making contact, breaking contact, moving to a new position, making contact, dragging, breaking contact is the cyclical part of the cross bridging. Here we can look at or observe the difference in the staining patterns as these bands shorten. So here's a relaxed sarcomere, and we can observe the width of the I bands, right? That light staining region. Remember, actin is a thinner protein, so it's going to give a lighter staining pattern. It's anchored here at the Z disc, which give a slightly darker staining pattern. The H zone likewise has myosin. It's going to be slightly darker than the actin, than the I band, but because myosin is thicker than actin, but it's also going to be slightly lighter than the actual area of overlap where we've got both proteins present. So the H zone shortens and eventually disappears actually as all of those actin filaments get closer and closer together. And the I band also shortens as the area of only actin also gets smaller and shorter. And the A band, as we can represent here, right along the center, stays the exact same. Now, the M line and Z lines do not change. They're static structures, meaning that they're not shortening or lengthening. They're not moving or sliding. They're static structures which are anchoring these proteins centrally. Okay, so they're not going to change in size. So let's get into the details of this cross-bridge cycling process and how we actually use this to generate force. So we describe it as being the cyclical formation and breaking of interaction between actin and myosin. This is what results in the sliding, and I keep using the word dragging here so you really understand what's happening, the sliding of the thin filaments towards the M line or the center of the sarcomere. And this is really brought about by myosin, right? We said myosin is the one that has the ATPase site, the site to bind ATP to energize this whole thing. And actin is kind of just taking a passive role in all of this, kind of just chilling out and being dragged towards the M line. So the myosin head has two states. It's got a high energy state where it has ADP and a hydrolyzed inorganic phosphate bound to it at that ATPase site. And in this state, it has a high affinity or attraction to actin. So it really wants to bind to actin in its high energy form. In its low energy form, it's got ATP bound to it, so it's not hydrolyzed, it's the full ATP. And this is in its low affinity conformation. So here it doesn't have much of an attraction or an affiliation for actin, okay? And we'll see how these two states or these two forms of the myosin head result in the cyclical process of this cross-bridge cycling. And so the movement or the dragging of actin by myosin relies on the hydrolysis of ATP to energize this process. And so we can speak about this analogous to rowing a boat. If you've ever been in a boat or in a canoe and you've used oar paddle to paddle or to move water or to move around in that water, we can consider that scenario synonymous to what's happening with cross-bridge cycling. So we've got the linking of the thin and thick filaments synonymous to your oar paddle making contact with water. So that's kind of the analogy there. And then we can think about the different aspects of this process. So you initially make contact with the water, right? You stick your oar paddle into the water. That's the interaction between actin and myosin. You then drag water behind you, or you propel yourself forward by pushing water behind you. That is synonymous with myosin dragging actin to the center or closer to the center of the M line. You then take your oar out of the water, so you remove your oar paddle from the water. That's synonymous with actin and myosin breaking or detaching from each other. And then you're going to reposition your oar paddle to a new spot in the water to move more water, behind you to propel yourself even further. And so that is synonymous with the myosin head moving to a new position along that actin filament in preparation to make another spot of contact and drag it even closer. Okay, and so that happens over and over and over again. So it's going to make contact, drag actin, separate or detach, move to a new position, make contact again, drag actin again, and that goes on and on. And so what I really want to underscore here is that the shortening of the sarcomere doesn't happen in one swoop, but it's just a cyclical moving of actin closer and closer and closer to the M lines until the entire sarcomere is at its maximum contracted state. So let's go through the steps involved in that process. So the steps of cross-bridge cycling. So there are 5 steps involved here. We start off with the interaction of actin binding to myosin. So that's kind of step 1. The myosin head is in its high energy form. It's got ADP bound to it and that inorganic phosphate. So remember we said that when the inorganic phosphate has been sort of hydrolyzed and sitting, waiting to give that energy to this process, that's when the myosin head is most attracted to the actin. So they're going to make contact. And then in this state, they really have that affiliation. This has to have calcium present. I'll talk about how calcium comes into play here. So that's step 1, the binding of actin to myosin when myosin is in its high energy form. Then we've got the releasing of that inorganic phosphate, and that brings us to step 2. This is where we have the power stroke. And so because we have that phosphate released off, we talk a lot about the energy that's stored in that third phosphate of ATP. When that phosphate is released off, it donates the energy for myosin to drag actin towards the center of the sarcomere, towards the M line. And so as it drags actin, we can see that it's now going to move to a different position as it drags actin, and that's going to be the power stroke. That's what's shortening the sarcomere gradually. Then the ADP is released off, and when the ADP releases off, that brings us to step 3. Step 3 is called rigor, and this is when myosin is back in its low energy form, right? It doesn't have a new ATP bound just yet. And so here, myosin and actin are pretty much stuck to each other. This is why we call this rigor. In this state, the muscles are in this extremely rigid, contracted position. And this is why after someone dies, the muscles stay in this way, in this form. This is called rigor mortis. This sets in after about 3 to 5 hours. And so the muscles stay in this really stiff, really rigid position because actin and myosin are tightly bound to each other, and they will not be unbound until a new ATP comes in and puts that myosin head back into its de-energized state to where it doesn't have an attraction or affiliation for actin. So at the rigor state, we're just waiting for a new ATP to come in. And as you would imagine, after someone expires, there's no ATP being produced. And so all of the muscles are stuck in this rigor position, step 3. And this is what is resulting in that rigor mortis postmortem. So now we've got a new ATP coming in. That new ATP brings myosin back to its low energized state where it doesn't want or doesn't have an attraction or affiliation for actin. And so it's going to unbind away from actin, and it's going to get ready to hydrolyze that ATP. That ATP now is converted to ADP again, and the inorganic phosphate kind of just chilling out, waiting to give the energy to the power stroke phase. And so the myosin head now gets into its cocked position. So it's going to reach up once again in order to make contact with actin. And this entire process will go over and over again just by the energized states of that myosin head, going from its low energy state to its high energy state in that cyclical fashion. Excellent, excellent question. So someone is asking, between steps 3 and 4, where does ATP come from? So we're going to talk about how ATP is produced. So there are lots of mitochondria. We spoke about the structure of the muscle fibers, lots of mitochondria that are providing the ATP that's needed for this process. And so ATP is going to flood the cytoplasm and bring about this muscle contraction. And we'll talk about how calcium regulates the turning on and off of this process, right? So the ATP is coming from the mitochondria that's in the myofibril, and that is what is providing the energy to bring that myosin head back to its low attraction state for actin. Okay, excellent question. So ATP and calcium are going to be the 2 important players of regulating this process.